If you've ever asked a mathematician what the most important constant in math is, or just anyone really, the three most interesting candidates would be E, pi, or I. And those are the ones that come up the most often. So E is Euler constant, pi is pi, and I expect you know it, and I is the imaginary constant, which is the square root of -1 for complex numbers. And if you watch a lot of math videos, and you probably do if you're watching this, then you'll probably know that e to the pi I is equal to -1. And that's called Euler's identity. And like that, it looks a little weird, and maybe you know why it looks a little weird and what it actually means. But it looks weird because we're not used to taking exponentials to some complex power. And the reason is that we're not actually really doing that. It's not like we're multiplying e pi I times or something. And so we'll see exactly what this expression means and kind of settle the debate in saying that what's most important isn't these constants, but it's really the exponential function itself. And I wouldn't be lying if I was saying that the exponential function is really the most important function in mathematics. So for real numbers, right, what we already know of the exponential function, it looks a little something like this, and it's a nice upscaling curve like this, and yeah, the exponential function, you've probably seen a lot of it, especially with corona. You've probably seen it for a number of cases increasing or something. For the complex case, while it's more complex, you probably don't even know what exactly this graph is trying to say, and you'll hopefully understand what it means around the end of this video. And so that's kind of what we're going to try to build towards, on top of a plethora of other results that we're going to have about the exponential function, which is really only a piece of what we could say about it. So to motivate the exponential function, we're going to start with this differential equation. So what it says is we want the derivative of a function to be equal to the function itself. Now the reason we'd like to do something like this is that, such a property would be really, really useful to solve differential equations in general. And as we'll see around the end, differential equations that are going to involve this function come up all around in physics, whether it be harmonic motion or just, simple linear equations. You're always going to have this you're always going to need a function to be its own derivative to solve these. And so that's a big motivating factor for actually building up the exponential. So to build this up, we're going to kind of assume it's a polynomial, okay? So we can start with the simplest polynomial, which is just a 0th degree polynomial, and so a constant. And we're going to say the constant 1, okay? Now if you take the derivative of 1, you get 0, so obviously 1 is not its own derivative. So we need to add to it something whose derivative is 1, so the integral of 1, basically. So we add z to it, because the derivative of z is 1. So now if I take the derivative of 1 plus z, I get 0 plus 1. And sure, I get this at the top, but I don't get the function I'm on now. I don't get 1 plus z again. So I'm going to append another term, and this term's derivative is z. So now I've got 1 plus z squared over 2, and if I take the derivative of that, I'm going to get 1 plus z. But once again, it's only the thing on the top, and we want 1 plus z squared over 2. So we're going to keep along this logic and, add z cubed over 3 factorial plus z to the 4 over 4 factorial, and these factorials come up because we're going to have 2 times 3 and then 2 times 3 times 4, because every time we're integrating here, we keep this constants we already had, and we have to append this new constant for a new degree. And so that's what we're going to start off with. We're going to say, okay, well, maybe the exponential function is this infinite series here. And what this infinite series would really mean, you'd know if you watched my power series video. And so that's what we're going to try to look at now is, does this power series actually converge? Because if it doesn't converge, then there's no point thinking about it at all. So for us to see if it actually converges, we're going to have to look at the cauchy-hadamard formula. And if you remember that, it basically says that 1 over the radius of convergence is equal to the lim sup of, and in this case, it would be the absolute value of 1 over n factorial to be 1 over n, as n tends towards infinity. And honestly, we don't even have to worry about the sup here, or about the absolute value, because, the absolute value of a factorial is a factorial, since they're always positive. And yeah, we're not going to worry about the sup at all, because in fact we can evaluate the limit in itself, and the lim sup is always equal to the limit if it exists. So to do this, we're going to start by looking at n factorial squared. And rearranging a little, if we have the first factorial in blue and the second factorial in yellow, and we kind of arrange them in opposing orders, then we can have 1 times n times 2 times n minus 1 times 3 times n minus 2, and so on, up to n times 1. So we've kind of flipped around here. And so now we realize that each term in here is of the form k times n minus k plus 1. So here, for example, k is equal to 2, and this here is n minus 2 plus 1, so n minus 1. Okay? And I want to show that this is bigger or equal to n, no matter what the k is, as long as k lies between 1 and n. And to show this, well, if we rearrange a little, we've got n times k minus 1 is bigger or equal to k squared minus k. Because I've got nk here, I've got an n here, so I can subtract the n onto the other side to get n times k minus 1. And I can move my k squared, well, minus k squared to the other side to become k squared, and then k to the other side becomes minus k. And now if I divide by k minus 1, and that's why we assume that k is bigger than 1, I've got n is bigger or equal to k. And you can check the case where k is equal to 1, it still works, right? So, what that means is that each of these terms here is bigger or equal to n, which means as a whole this product is bigger or equal to n to the n, because there's n such terms. So n factorial squared is bigger or equal to n to the n. And so now if I take the 1 over nth power and the 1 over 2 power, so I guess 1 over 2n, I do it to the power of 1 over 2n, then I'm going to get n factorial to the 1 over n is bigger or equal to the square root of n. And the square root of n tends towards infinity as n tends towards infinity, so this here is going to tend towards infinity as well. So hence we have that the limit of n factorial to the 1 over n is infinity, and then with some simple limit identities you get that the limit as n tends to infinity of 1 over n factorial to the 1 over n, and I've just put the 1 over n in bigger parentheses because 1 just stays 1, that's going to be 0. You can kind of think of plugging infinity into 1 over infinity that gets you 0, sort of. So that means that r here is going to be infinity, because r is, well, 1 over r is equal to 0, so by the convention of power series radius of convergence, you get that r is equal to infinity. So thanks, Cauchy-hadamard. So what that means is that exponential function has this power series representation over the entire complex plane, and that's really, really powerful. We've got an analytic function that's that exists over the entire complex plane with a simple power series representation. So we've got an entire function, and entire functions are kind of rare. So, absolute convergence and power series that converge absolutely converge give us a nice multiplication formula for infinite series. And I'm not going to prove this multiplication formula here. It's a standard result from analysis, and if the proof isn't that nice, I'll just leave it out. And so we've got, if I have a product of the infinite sum of an and the infinite sum of en, and I require that an, well, this sum here converges absolutely, then I've got that this this product is going to be equal to a sum of a sum, and the sum inside it is going to be finite depending on the index. And then I've got this sort of, well, it kind of looks like a convolution of the two sequence terms. So now let's look at what that means for our exponential function. And note, we're still using the notation of f and not of e. So now if I have f of a times f of b, well, I can just plug in the power series representation. And now because I know they absolutely converge, I can put them together into this double series here. So the n's here becomes k, and the n's here become n minus k, like this. Now this doesn't get us really far, but if we note that k factorial times n to the minus k factorial is the denominator of the binomial coefficients, right? If we multiply this here by n factorial, we get the binomial coefficient. So I can multiply the inner series by n factorial and divide it by n factorial so that I don't change anything. And I'll take the division by n factorial outside of the series since n is not the index of the inner series. So I've got 1 over n factorial times the inner series, and here I've got n choose k because that's the binomial coefficient we just got. And we haven't changed anything about a and b. And now you'll note that this series here, you might recognize this as the binomial expansion for the nth power. So that's going to be a plus b to the n and all over n factorial. And so now you'll note, if I compare this back to our original power series, well, it's like if I plugged a plus b inside z. So that proves one of the most important properties of the exponential function, which is that the product of exponentials is just an exponential of the sums. So fa times fb is just f of a plus b. And that's a very, very powerful property. So now we're finally going to introduce e for some ease of notation. So we're going to define the constant e, and this is a definition, as this power series that we had evaluated at 1. So it's just the infinite series of 1 over n factorial. So that's one representation of e you can have. And you can prove that that's irrational and even transcendental. And I guess you can compute, decimals of e just by taking the first few terms of this series. And so we're going to assign this notation, e to the z. Notes this is not the constant e to the zth power, right? It's just some notation. And we're gonna write it like this. We assign this to be the power series that we've looked at up till now. So keep in mind, this is a notational shorthand. It doesn't actually mean taking e to the zth power. Though for real numbers, it coincides with that. So if I take the derivative of this, by the limit definition of a derivative, I've got e to the z plus h minus e to the z all over h. And here I can use the identity we just proved that e to the z plus h is e to the z times e to the h. And so I can factor out the e to the z outside of the limit because it doesn't depend on h. And so now I've got the limit as h approaches 0 of e to the h minus 1 all over h. And e to the h minus 1 over h, you can prove that this limit approaches 1. You could just plug in h inside our power series representation. And by subtracting 1 and then dividing through by h, you'll have infinitely many terms that go to 0, and you'll only be left with the first term, which is 1. And so that's how we get that the limit ends up being just e to the z. So we get that the derivative of e to the z is e to the z. And so we've properly justified our original motivation that the function is its own derivative. So let's look at a few things. If I plug in 0 into the power series, I get 1. And what that's going to imply is that the reciprocal of e to the z, so the multiplicative inverse, is going to be e to the minus z. Now why is that? Because if I take e to the z times e to the minus z, by the identity we showed earlier, that's e to the z minus z. And so that's e to the 0, and we just showed that that's equal to 1. So that means that these two are multiplicative inverses. Now, this whole mumbo jumbo, basically what I've done is I've taken, well, I say x is real, but x can be complex really here. Except for our case, we really care about it being real. But if I take x and I multiply it by I in the exponent, well, in the function, well, if you split things around, you're going to get some terms for all the terms that are of even degree. The I is going to disappear because it's going to be either squared or to the 4, or, as that periodically goes on, you're going to have 1 or minus 1, so that's why you get this minus 1 to the n term. And these two n terms specify that it's, at the even numbers, well, at the even degrees. And then for the rest, it's going to be the same, except you're going to have an extra I term in the front, and it's going to be for the odd degrees, right? So all I've done is really I've just plugged this into the power series, and I've split things from the real part and the imaginary part. You can do this for yourself. So what that implies, if it's instead of ix, I have minus ix, so I times minus x. Well, minus x to the 2n is just x to the 2n, because this is even. But minus x to the 2n plus 1 is x to the 2n plus 1 times minus 1. So I can put the minus 1 at the front here, which turns this plus into a minus. And so what that means is, if you remember the definition of a complex conjugate, well, e to the minus ix is the complex conjugate of e to the ix. That's kind of cool. So not only is it going to be its multiplicative inverse, but it's also its conjugate. And so that gives us something very nice, because now we can take the squared magnitude, and for complex numbers, that's defined to be the number times its conjugate. And now we know the conjugate is e to the minus ix, and since we know these two are multiplicative inverses, this is equal to 1. So the square magnitude is equal to 1, which means the magnitude is equal to 1 on its own. So that means that e to the ix, for real x in this case, that's what we want to be careful about. We want these to be real x's, because otherwise we can't really apply this argument of minus ix here. Or to be fair, we just can't really split it in terms of real part and imaginary part like this, because you'd have some extra I terms inside of the x. So for real x, e to the ix is going to be equal to 1. Well, its magnitude is going to be 1. And so now, using our identity we had before, I can split this x plus iy into e to the x times e to the iy. I'm still looking at magnitudes. And since we know now that this here has magnitude 1, then the magnitude of this general exponential is just the magnitude of e to the x, where x is the real part of the original argument. So what that means is that if e to the x plus iy is equal to 1, then we need to have the real part of that argument be 0. And more generally, if the magnitude is equal to 1, well, that's if and only if the first part is equal to 0, right? But specifically, I wanted to for 1 here. So let's look at some more properties. To make notation even easier, we're going to assign, once again, this isn't your regular cosine. Well, it is, but we're defining it as such, right? Imagine you've never seen cosine before. We're assigning it to be the real parts of the exponential, and we've calculated the sum in the slide before. And similarly for sine, this is going to be the imaginary parts, okay? So these are the common Taylor series that you might know for cosine and sine. And so now e to the iz is equal to cosine z plus I sine z. So really, sometimes you see this in class and complex numbers, and you're like, wow, this is insane. There's a connection between the exponential and the cosine of the sine function. And yes, there is, but it's more so by definition than by development, if you will. Though to be fair, you could start by defining the trigonometric functions differently and then come to this, but this, in my opinion, is one of the more natural definitions. So now if I take the derivative of this, right, well, by the chain rule, because I know the derivative of e to the z is e to the z, then the derivative of e to the iz is going to be I times e to the iz. And so now I take the derivative of each term in here alone, so cos prime of z, so the derivative of cosine, and then sine prime of z times I. I is just like a constant, so it can be treated like in regular differentials. And so now what that tells us is if I divide through by I, I'm going to have minus I cosine prime z here, and here I'm just going to have sine prime z, and then I can compare it, the real and imaginary parts, with our first equation here, to get that the derivative of cosine z is minus sine z, and that the derivative of sine z is cosine z. I don't know where there's a prime here, it shouldn't be there. So that already gives us our regular interpretations of the derivatives of the trigonometric functions, which often is just given in class, and you don't really know why those derivatives are true. So now plugging in 0 into the power series of cosine and sine, you can quite easily get that the cosine of 0 is 1 and the sine of 0 is 0. Okay? Now this is a little bit harder, but the cosine of 2 can be shown to be smaller than minus 1/3, and that's because you can plug in 2 to the first few terms of cosine, and note that after a while the terms are going to be decreasing. And then just doing some rearrangement, you can show that the cosine of 2 is less than minus 1/3. I can leave that to you as an exercise, if you're not too sure about why this is true. So what that means is that we start at 0, right? If I look at the graph of cosine, which we don't really know yet, well, at 0 it's equal to 1, okay? And at 2, it's smaller than minus 1/3, so it's somewhere down here. What that means is by the intermediate value theorem, well, if it's continuous, and we know it is, because it's differentiable, because remember, e to the z is entire, which means its real and imaginary parts are also going to be holomorphic, or, well, yeah, differentiable. And so by the intermediate value theorem, we have to have a value, well, an argument of cosine between 0 and 2 that's equal to 0, because it has to cross the x-axis at some point. So we define that as p, right? And with 0 is less than p is less than 2. And so it's p such that cosine of p is equal to 0. And so now we define one of the most important constants in mathematics, pi. And we say, pi, okay, it's a nice little piece of notation, but it's really just going to be 2 times p. And so for everyone saying, hey, we need to have tau and not pi and whatever, well, if you ask me, we really just need to have pi over 2 as the real cool constant. It's the one we deserve to have, not tau or pi. We should be looking at p instead. So now, what that tells us is that sine pi over 2, and so pi over 2 is just p, but I'm going to write it pi over 2 from now on, is either equal to 1 or minus 1. Why is that? Because at pi over 2, well, we just defined that as cosine being 0, and we know that e to the I pi over 2, we know that that has magnitude of 1, because that's something we showed earlier, right? This is a real number, and it's multiplied by an imaginary constant, so it has to have magnitude 1. But it's also equal to, if you take the real part and an imaginary part, well, cosine squared pi over 2 plus sine squared pi over 2. And you take the square root of all that. And so you know that this here is equal to 0. So if you want the square root of a square number to be 1, well, that number has to either be 1 or minus 1. But now we can show that it's actually equal to 1, because we know that the derivative of sine of x is bigger than 0, for 0 is smaller than x is smaller than pi over 2. That's because the derivative of sine of x we've shown is equal to cosine of x, and we just showed here that cosine of x is bigger than 0 in that interval. So the derivative is bigger than 0, which means it's increasing. So if it starts at 0 and then increases, right, and it doesn't decrease at any point from 0 to pi over 2, then it can't possibly be minus 1 at pi over 2, so it has to be 1. So that's how we get this result here. And so now using this, well, e to the I pi over 2, now that I can just plug in pi over 2 into cosine and sine, I'm just going to get that e to the I pi over 2 is I, okay? And then e to the pi I is going to be I squared, which equals minus 1. That's because I just take e to the I pi over 2 times e to the I pi over 2, which gives me e to the pi I, so I get I squared. And by definition, I squared is minus 1. And in general, e to the 2 pi I n is going to be minus 1 to the 2n, which where I've just put minus 1 to the power of 2n here, and that's just going to be equal to 1. Okay, and n is an integer in this case. And so now we can kind of start looking at this, right? If I kind of imagine a unit circle, and this will also be very intuitive if you just kind of take for granted that the cosine and sine coincide with our regular functions. If you imagine a unit circle like this, well, if this is the real axis, and this is the imaginary axis, right? Well, okay, we've got I here. Let's write I. We've got 1. We've got minus I 1. And so now you'll see our angles coincide. At angle pi over 2, well, e to the I pi over 2 is 1, okay? At angle e to the pi I, we've got I squared, it's minus 1. And as a matter of fact, you could show that e to the I 3 pi over 2 would be minus I here. And so in fact, and I'm just going to tell you this, e to the I times some angle, well, some number, right, is just going to be, on this unit circle, add the angle of that number. So e to the I theta is just a number on this circle. And again, that's kind of, it's easier to see if you just take for granted the fact that the cosine and sine coincide with our actual values. Oh, and yeah, you can also show that e to the z plus 2 pi n is equal to e to the z because of this identity here. So that means that e is periodic with 2 pi I, with 2 pi I period. The n is just any integer. So we take the smallest integer, which would be 1, and so it has period of 2 pi I. So that's kind of cool. It's a periodic function as well, which also explains the periodic behavior of sine and cosine, and why we'd want to use e in physics a lot, especially for things like oscillatory motion. So there's still a lot of results you could show for this function. We've already showed a lot of stuff, and I think it's really cool to, get these results from scratch. So you can try these results for yourself. For example, you could look at the addition formula in the Pythagorean identity for the trigonometric functions. So if you can show that cosine squared x plus sine squared x equals 1, and this one's really not too hard to do from what we've done till here. And you can show also the addition formula, so cos of a plus minus b, and I'm not going to write what it's actually equal to because it's too long, and then sine of a plus minus b. These are kind of nice results to show. So I'll leave out those ones to you. You could also try and prove, now this is a little harder, that fx, well, the map fx e to the ix for real x is surjective, which means, it maps exactly onto the codomain, with codomain the unit circle, which means if the whole real line gets mapped to the unit circle, and that's going to be useful in interpreting the graph I showed at the beginning. And you can also show that for any complex number w, or omega, I guess, I wrote w, but yeah, which is not equal to 0, there exists some complex z that's not unique, such that e to the iz is w. Now, not unique is important. What that tells us is that the logarithm, well, the analog of a logarithm for complex numbers, is actually multi-valued in the same sense that the square root is. We don't have a single value, and we look at things called branches or sheets, and usually we look at what's called the principal branch. And that all has to do with the fact that e is periodic, right? You also know that arcsine and arccosine can sort of be multi-valued, but we have to restrict them. Well, here it's kind of the same thing. So you can also prove that e to the iz equals 1 if and only if z over 2 pi I is an integer. We've shown one direction. The other direction is a lot trickier, so good luck with that. And honestly, there's a lot of things you could try to prove for yourself, I mean, if you want to try to prove that e is irrational, or that pi, I'm not sure how the pi proof works, I'll have to look that up. But the e proof for irrationality is doable. It's not very easy, though, from what we've done already. But yeah, you can try that. So let's finally look at our graph here. So what I've got is I've got this line here, which I drew in purple, and I'm drawing over it in red, very poorly. What I'm trying to show is that this line here is the line in the complex plane with real part 0. And the dotted line with the same color is the unit circle. So what I'm trying to say here is that this line gets mapped to this circle. Okay? And so basically, the way that it works, and that's because, e to the... We already showed that if the real part is 0, then it's going to have a magnitude of 1. And then if you let the imaginary part go along its period, then this line is going to wrap around this circle a bunch of times. And so basically the way it works is if I take lines on the right of it, well, they're going to be outside this circle. And so, for example, this line here, right, is going to be this circle here. And this line there is going to be all the way out. And then the lines inside here, they're going to wrap inside, and particularly this line there is going to map to this line here. and this line here is going to map to the smallest line I've been, the smallest circle I've put inside. And so it's like you're folding the plane onto itself. So you're kind of grabbing it at 0 and moving it towards the right, and then you're kind of folding the right-hand side of the plane while wrapping it around this line here, and all this left hand of the plane just gets squished inside into a magnitude 1 disk. I think that's a really cool action. And I think Free Blue and Brown has a very nice visualization of it. I don't have any nice visualization software. Well, fair enough, he made his own. But so this was the best kind of visualization I could give you. And so, E turns up everywhere. I mean, it turns up in the Fourier transform, which you might have heard about, which is very useful in decomposing functions into sines and cosines. And so, obviously, now that we've seen that sines and cosines are so intrinsically related to the exponential, well, we like to use the exponential instead. In nuclear decay as well, half-life decay, which you may have seen in high school, or the normal distribution, which you may have seen in high school as well, which describes so many statistical phenomena. You also see it in the Poisson distribution, for example. So E is really a powerful number, a powerful function, most of all. The number itself is actually not all that interesting. It's not the number that turns everywhere, it's the function that turns everywhere. The number is just kind of a byproduct of that. So I hope you enjoyed this video and that you've learned to love E more. And yeah, I think the next special function I might be going over will be the gamma function, which is a lot more complicated, but just as interesting. So see you then.